Your homework last night was simply 3 questions, all based on that relative motion in 2 dimensions. I'm going to just do a quick little review, and then we're going to go over all 3 of those questions here. Remember, when you're solving relative motion problems in 1 dimension, you add up the vectors, right? You got a wind that's blowing to the north. You're heading to the north. Well, you have to add up those vectors to get the overall velocity, right? Okay. If you got a wind of 50 kilometers per hour to the north, but you're heading at 200 kilometers per hour to the south, add them up. 50 plus negative 200 gives me negative 150. So we add them up. Now, if we have a relative motion problem in 2 dimensions, then what are we going to do with these vectors? Add them up. We do the same thing. But when we add up vectors in 2 dimensions, we've got to add them up vectorially. So we've got to end up doing that Pythagorean theorem and then that inverse tan function to get the direction of them. There's a couple things that you got to remember, though, before you get to that triangle, and that is which vectors are which. Which vectors are the solid lines? Which vectors are the dotted lines? The rule of thumb is this. If it contributes to the real velocity, then it's going to be what? Solid or dotted line? Solid. In other words, if it's the wind speed, that contributes to where I go. If it's where I aim or head, that contributes to where I go. Okay, if it's the airspeed of an airplane, how fast it could travel without a wind. Okay, that contributes to where I go. Okay, those are all going to be solid line vectors. Finally, the dotted line vectors are where I actually go, or where I actually want to end up going. So let's draw the diagrams for all 3 of these, and then let's solve them here. Question number 1 on your worksheet says, the pilot heads her plane with a velocity of 250 to the north. She heads, she aims, solid or dotted line? Solid line, good, Zach. So she heads 250 kilometers per hour to the north. Let's make that a solid line, 250. There's a wind of 100 blowing to the west. Does that contribute to where I go, or is that where she actually goes? That contributes, right? So that's going to be solid or dotted? No one? No. If it contributes to where I go, it's going to be solid. Good. So we're going to make that 100 this way. Notice it's drawn front to back. Always has to be drawn front to back, right? The resultant vector is going to be drawn right here. Let's find the value of that resultant vector. Call it R for resultant. Call it C. Doesn't really matter. What does C end up being there? Pythagorean theorem, right? 2.69, 269? Yeah. Oh, yeah, 269 kilometers. And theta would be the inverse tan function of opposite over adjacent 100 over 250. Who's got the value for that? 21.8. And we're going to express that 21.8 west of north, because it's north and then it's west of north, or west from north. Good? What would have happened if you had to draw the x component first? Could you have done that? Drawn the wind and then where she heads? Sure. You would have just gotten an angle of about 67 degrees, 67.2 degrees, and it would have been north of west instead of west of north. 2, the airspeed of an airplane headed north is 40 meters per second. So we're heading to the north at 40 meters per second. Solid or dotted line vector? Caitlin, solid or dotted? Good. There's a wind gust blowing to the west of 15, oh, that's a fast wind, 15 kilometers per second. Anybody catch that? A little bit of a typo there. It meant to be meters per second. Wow, that would be one fast wind. You changed it to 15,000 meters per second? Did that not strike you guys as being a little bit odd that the wind was that strong? All right, so guys, I'm going to go with 15 here. Your number is going to be different, obviously. We're going to go about solving this the same way as we solved this one. Okay, I'm going to get somewhere like, I don't know, 43, 44, 43. Okay, you're going to get somewhere like pretty close to 15,000, 15,000 and something, right? Okay, the angle, my angle is going to be, I don't know, 20, 30 degrees, 21 degrees. West of north, your angle is going to be pretty much 89.9999, something like that. Pretty much 90 degrees, right? Make sense? finally, number 3 says a boat whose speed in still water is 2.5 meters per second. So that's how fast I can aim, 2.5 meters per second. Okay, that's going to be a solid line vector. The river is flowing at 1.2 to the south. That's solid as well. What's the velocity of the boat relative to the shore? That's what we're trying to find, the dotted line vector, when the boat is headed south. We don't even have to draw a diagram for this one. Look, the water, I can head at 2.5 to the south. The water is 1 to the south. Add those up, we get 3.5 to the south. There's nothing crazy to do with that, right? That's a one-dimensional problem that you could have solved in grade 7. Yeah, sorry, it's 1.2, not 1.0, right? Yeah. I said you could solve that in grade 7. Well, apparently I can't solve it right now. But if I had written the right number down, I would have got it. Good, thank you. Boat is headed north. Well, if I got the boat heading north, but the river current is to the south, I'd like to draw that front to back. It's kind of hard to draw it perfect there because it kind of comes back upon itself, right? And 2.5 plus negative 1.2 gives me 1.3 meters per second to the north. And C is the only one that we have to do 2 dimensions with. We have the boat heading 2.5 to the west. We have a river going 1.2 to the south. And then the resultant vector is the dotted line, okay, where we actually go, or the velocity relative to the shore. What's C there? Square root of 1.2 squared plus 2.5 squared. 2.8 meters, thank you, Zach. And meters per second, right? 2.8 meters per second, because it's a velocity problem. And the angle is going to be, I don't know, I'm going to say 20 degrees, 30 degrees. What is it? Did you get it? Ethan, you, yes.
Me?
Yeah. 25.6. We're going to round that to 26 degrees, and that's going to be south of west.